All right, so today we're going to be talking about performance and limitations. Unfortunately, this is a technical subject area that not a lot of people pay attention to, and it ends up with a lot of fatalities and accidents when people don't do their performance calculations in regards to the ground roll on takeoff, ground roll on landing, how they actually distribute weight in the aircraft, what kind of performance they're going to get on a given day. Because day to day conditions change, and we need to know whether or not the air is getting more dense or is it getting less dense, because that's going to drastically affect our performance. Which brings us into the first thing: what affects our performance, and that is air density. So we kind of measure performance off of three things: the thrust that a propeller produces, more dense air, more thrust. It's kicking more air back. And then we have lift of the wings, more dense air, more lift on the wings, so higher pressure under the wings to, we talk about Bernoulli's principle and whatnot, lower pressure on top, creating more lift. And then we have power. So we know that four-stroke cycle, we need a good fuel and air ratio to actually create that combustion cycle inside of the cylinder to produce power. If we have more dense air, higher power, pretty much. So three things there. So is the air getting more dense or is it getting less dense? And it's affected off of, really four things. We're talking about the first three here. First one's going to be height. Height, if we look at the Earth here, if we draw out a radius from 18,000 feet MSL, 50% of the air molecules in our entire atmosphere exist under 18,000 feet MSL. So you can see as we go up in altitude, less dense air exists. Not in the sense that, it is the same amount of air when we get into human factors and how we actually breathe this stuff. But the amount of air that we can use for engine power, lift, and propeller thrust drastically decreases because it's less dense. It's a little bit more complicated than that, but that's the gist of it. So as we go up in altitude, whatever elevation we're starting this takeoff roll at, whatever elevation we're actually trying to initiate, or trying to land the plane, it's going to drastically affect our performance. And the performance charts for the pilot information manual are going to go ahead and account for this. So we have height, then we have heat. So heat is going to make the air dense or less dense. So we have a column of air that is very cold. When air gets cold, it has a tendency to kind of compact itself, become more dense, sink to the bottom. And so we have more air molecules on a colder day, all other variables aside, to use for propeller thrust, wing lift, and engine power. And then on a hot day, these air molecules have a tendency to disperse, kind of move around. They have more kinetic energy and they're moving around, not as dense. So on warmer days, like the ones we get out here in Phoenix, 100, 115 degree days, less performance. That means longer takeoff rolls. That means longer ground rolls on landing. That means less takeoff less climb performance on takeoff. So less lift on the wings, less propeller thrust, and less engine performance on less dense days, so hotter days. Height and heat are going to be taken account for in, like I said, Chapter 5 of the Pilot Information Manual, which is what we're going to go through. This section, performance limitations, is going to be kind of broken up into two things. We're going to talk about Chapter 5 first, how we actually do our 91-103 pre-flight action, which is our takeoff performance of intended runway use. And then we're going to go into weight and balance, how loading things in the aircraft changes our performance, and how important it is to be within a center of gravity envelope. But right now we're just going to go into the Chapter 5 stuff with performance and how our aircraft actually performs on a given day. So height, heat, and another one that is accounted for in Chapter 5 of the Pilot Information Manual is pressure. So we talked about how as we go up in altitude, less and less air that we can actually use for those three variables to increase performance. Pressure, we get air masses that have similar pressure properties and temperature properties that go ahead and meet, and they move along the Earth's surface. So if you have one coming into your area that is a lower pressure system, so less dense air, you're going to get less performance. If you have a high pressure system coming in, so a colder air mass that's coming in, you're going to get more performance. So that's just something that we actually have to be, cautious about. When we get that altimeter setting, when we fire up the engine from the ATIS or whatever, they're going to give us an altimeter setting, and we'll get into the standard datum plane and what that actually means. But it's very important because air masses move across the Earth's surface, and we talk about the height, heat, and the last one, humidity here, but pressure is a big variable with that as well. So we talked about pressure, heat, and height. Now we have humidity. And Chapter 5 of the Pilot Information Manual doesn't really take humidity into account, but it's a big factor. We fly out here in Phoenix, super dry heat, not a lot of water molecules in the air. If you fly south, though, it drastically affects your performance. Because if you get a hot, humid day, not only do we have these air molecules that are really, sparsed apart, moving around, we also have air masses that are full of water molecules, making less room for air molecules to actually exist there. Our engines don't produce power off of water, we don't produce thrust off of water, and we don't produce lift off of water. But unfortunately, the Pilot Information Manual doesn't really take account for that. It's just something you have to be aware of. So we talked about whether the air density is getting more dense, less dense, the variables that go ahead and affect that: pressure, height, heat, and humidity. So how do we know for a given day if the air is more dense or is it less dense? How do we actually calculate that, and what are we actually calculating that from? How are we taking these measurements? Well, that's going to play into the International Standard Atmosphere. So the ISA, International Standard Atmosphere, consists of a few things. So it consists of standard day pressure being 2,992 inches of mercury. So on a standard day, 2,992 inches of mercury is going to be the pressure level at sea level. We're taking all of these measurements from a theoretical plane at sea level. And then we have 15 degrees Celsius. So not only at sea level does it have to be 2,992, it has to be 15 degrees Celsius. And then any change in temperature or pressure is going to move how we calculate where that standard atmosphere is at. What is that standard atmosphere? It's called a standard datum plane. And like I said, this is just a theoretical plane that we actually make measurements from. So if we have sea level here, let's draw some waves, and let's say it's a standard day. Let's say at sea level it's 2,992 inches of mercury, and it's 15 degrees Celsius outside. Our standard datum plane is going to exist at sea level. Now, the standard datum plane can move up or down depending on how the atmosphere actually changes. Is the pressure going up? Is it going down? Is the temperature going up? Is it going down? Also a variable with this, they say for every 1,000 feet in altitude that we go up from sea level, we lose an inch of mercury. So it'd be 2,892 here. Right here would be 2,792. So each 1,000-foot increments we go up, we lose an inch of mercury. Also, each 1,000 feet increments we go up in the atmosphere, we lose 2 degrees Celsius. So 13 degrees Celsius, 11 degrees Celsius, up. And that's just standard. So that's kind of how we're measuring where the standard datum plane is going. So how do we tell where the standard datum plane is for a given day? We have two performance calculations that we use to go ahead and calculate our performance. The first one is going to be pressure altitude. Now, a lot of people think pressure altitude, is something that we use to fly around. What's my pressure altitude? Where do I need to be, for a cruise flight? It's strictly a performance calculation. So these are theoretical numbers we're using to see what our performance is for a given day. Pressure altitude is our atmosphere corrected for non-standard pressure, so anything other than 2,992. And our density altitude is our pressure altitude corrected for non-standard temperature. So whatever we calculated here corrected for anything other than 15 degrees Celsius. And we know it rarely in Phoenix is ever 2,992, 15 degrees Celsius. So our performance is never going to be, that standard day performance. It's consistently changing. So We have pressure altitude. How do we calculate that? That's going to be our standard altimeter, 29902 inches of mercury, minus our actual altimeter setting. So when we fire up that aircraft and get that altimeter setting, in the example here we use 3002, and we'll do the calculation with it. But it could be 2792, it could be 2812, whatever it is. We can go ahead and calculate it using this formula. Then we're going to multiply it by 1,000, and then we're going to add our field elevation. So with pressure altitude, we're basically just finding out, pressure-wise, what does the aircraft feel like it's actually flying at? Because we know less dense air, lower pressure systems, we get less performance. And more dense air, higher pressure systems, we get better performance. So what does the aircraft actually feel like it's taking off at field elevation for this given day? So we'll do 29902, and let's say we fired up the aircraft and the ADA said, hey, the altimeter setting for today was 3002. So we know that it's going to be negative 0.10. Now we have to multiply that by 1,000, and that's going to give us negative 100 feet. So from this calculation, this is telling us that we have to subtract 100 feet from our field elevation because this is a higher than standard day, because we have 3002 and we know 29902 is the standard day. So we are out here at Goodyear. It's going to be about 1,000 feet, our field elevation. We'll go ahead and just make the math simple here. So our aircraft, pressure-wise, is going to feel like it's taking off at 900 feet, which is pretty cool. That means that the atmosphere is more dense, it's higher pressure, and we're creating more power, we're creating more thrust from our propeller, and we're getting more lift because the day, pressure-wise, is higher than standard, which is really nice. Cool, so that's letting us know that the standard atom plane, when we go ahead and get minus 100, it actually exists 100 feet above sea level, this 29902. So this is letting us know if we were taking off at 1,000 feet up here. Let's go ahead and get this stuff out of the way. Say this was our field elevation, and this is our aircraft, 1,000 feet, MSL. This is letting us know that the atmosphere for this given day at sea level is 3002. The standard datum plane actually exists 100 feet above that, and we have to go ahead and subtract that from our field elevation to get our actual pressure performance for that given day, if that makes sense. So we're actually going to be feeling like, instead of 1,000 feet MSL, that we're taking off at 900 feet MSL. And we know as we go up higher in altitude, we get less performance because of less dense air. So this is kind of a theoretical calculation that we're doing. So we have 900 feet here for our pressure altitude, but we know that it's rarely ever 15 degrees Celsius. Now with pressure altitude, when pressure changes, our calculations or our performance is just going to change a little bit. So with, we went from 1,000 feet to 900 feet for our pressure altitude. When we start changing temperature around, our performance, increases or decreases drastically. So pressure is going to be a big variable. We dropped to 100 feet, that's good. But let's say it was, 105 degrees Fahrenheit outside, 40 degrees Celsius. What's actually going to happen? So that's what density altitude is going to be. And that's going to be kind of the end of the calculation. We're using our pressure altitude being our atmosphere corrected for non-standard pressure, plus the outside air temperature minus the standard temperature at that field elevation times 120. So we have the pressure altitude here. We already calculated that for this given day. It was 900 feet. We know that's a higher than standard day. That's cool. We went down 100 feet, and we're going to get better performance pressure-wise for this day. Now let's pretend that it was 40 degrees Celsius outside. And that'll be about 105 in the Phoenix area, which is pretty common. What is our standard temperature at this altitude? Well, we know the standard atom plane at sea level is 15 degrees Celsius. We're going to go 1,000 feet up. We also know that we lose 2 degrees Celsius per 1,000 feet. So our standard temperature should be 13 degrees Celsius. You can see how out in Phoenix, how much higher we are than that standard day temperature. And then we're going to multiply this by 120. Let me just do some quick math on my phone real quick. So we're going to go 40 minus 13, multiply that by 120, which is going to be 3,240, and then we're going to add 900. So look what happened. Now our aircraft feels like it's taking off at 4,140 feet. So you can see how temperature drastically affects the performance compared to changes in pressure. Pressure does affect it, but look how drastic we went up. So we dropped 100 feet because it was a higher than standard day pressure-wise, but this temperature was so much higher than standard that we jumped all the way up to 4,000 feet, 4,140 feet. So if we're taking off in these conditions at 1,000 feet, our aircraft already feels like it's at 4,000 feet, which we talked about. The higher we go in the atmosphere, the less performance that we get. Less air molecules for propeller thrust, lift on the wings, and engine power. So those are the two calculations we're basically going to use for pressure altitude and density altitude. Pressure altitude we can also find by going in the aircraft and setting the altimeter to 29 or 902, and that's going to give you the height above the standard datum plane. So you can get your pressure altitude there. Density altitude, we can use this formula here. You can also use an E6B, can't really show you here. Super easy to do, there's a bunch of YouTube videos on it, and I believe the E6B actually shows you. It's a little column. You just rotate a couple cylinders on that electronic flight computer, and it can go ahead and tell you the density altitude for a given day. Also, you have density altitude conversion charts inside of the POH, and you just kind of go, it's just like a simple graph. You go from pressure altitude, read the left column, and it'll tell you your density altitude for a given temperature. But yeah, the main idea with this, standard datum plane, where we go ahead and take measurements from. We have the standard, but it's rarely standard. How do we go ahead and get an idea for our performance? Well, we have to correct for non-standard pressure, because pressure is rarely standard. And then we have to correct for our temperature. And you can see how drastic the differences are when we correct for temperature compared to the pressure. And that's basically going to be the gist of it. It's really cool, which I'll show you, Chapter 5 of the Pilot Information Manual. On the left column, it'll show you what pressure altitude is it for a given day. So it's correcting for that pressure. And then on the top column, it's correcting for temperature. And we're just kind of reading in between the lines there to give our performance, our ground roll, how long will it take for us to clear a 50-foot obstacle, stuff like that. But yeah. Now I just wanted to reiterate types of altitude. These are types of altitude, but these are performance calculations. These are not altitudes we actually fly by. These are altitudes that we figure out on the ground to find out what the aircraft's actually going to feel like when we start up the engine and start this ground roll. But we have a few different types of altitude. Get this stuff out of the way here. We have indicated pressure, density, then we have true and absolute. Indicated altitude is going to be the altitude that our altimeter indicates. If we don't go ahead and put that altimeter setting in there, it's not going to be correct, and it's not going to give us the height above our standard datum plane. So we got to go ahead and correct for that. Our pressure is going to be our indicated altitude corrected for non-standard pressure. Density altitude we went over was going to be pressure altitude corrected for non-standard temperature, which changes our performance drastically. Our true altitude is our actual height above sea level, which is commonly on the sectional charts referred as MSL, mean sea level. And then we have our absolute altitude, which is AGL, above ground level. Now we also have some airspeeds as well that I wanted to touch on before we jumped into the performance charts. Are indicated. So this is altitude, and this is airspeed. indicated, we have calibrated airspeed, true airspeed, and then we have our ground speed. And then there's also equivalent airspeed, but we won't get into that stuff. Indicated airspeed, what that airspeed indicator is indicating, kind of simple. Our calibrated airspeed, and there's actually a calibrated airspeed conversion chart inside of the pilot information manual. It's going to be what our aircraft is actually flying. So we could be flying an indicated airspeed of 55. It could actually be much higher than that for given flap settings, angles of attack, and there's a conversion chart in the pilot information manual to go ahead and convert for that. Calibrated airspeed is basically indicated airspeed corrected for position or instrument error. Like I said, flap settings, angles of attack on landing can go ahead and give you some deviations, but it's usually in your favor. So fly these indicated airspeeds regardless of what the calibrated airspeed is. It's kind of just a safety buffer as well. It gives you a few extra knots, even though, hey, we're flying just above stall speed. We're actually probably flying about 5, 6, 7 knots above that with our calibrated. Then we have true airspeed. This is going to be our calibrated airspeed corrected for the air mass in which it's flying in. So basically non-standard pressure or temperature, and which we can actually calculate on the airspeed indicator. If you go ahead and there's a knob, it's kind of hard to if we have the airspeed indicator, there's a knob that you can actually rotate to the temperature outside, and as we change the temperature, it changes our airspeed for the air mass we're actually flying in, because we know warmer air masses less dense, and then colder air masses more dense, and we can kind of calibrate that on the airspeed indicator. And then we have ground speed, which is going to be our speed over the ground, pretty much. If somebody had a radar gun on the ground and was tracking us, it would tell them how many knots we were going, or miles per hour. But yeah, that's going to just be the common altitudes we have, and then the airspeeds that we have. Just wanted to touch on those before we go into Chapter 5 of the Pilot Information Manual. Also, be aware of all your V speeds, your VXs, your VYs, VNO, VNE, flap operating range, all that stuff when we're talking about these performance calculations, just to get a good idea of how much we can actually stress this aircraft. Big one is maneuvering speed, which is going to go ahead and change with weight, which we'll talk about when we get into principles of flight. But understand, yeah, maneuvering speed is going to make sure you stall the aircraft before you actually break the wings off, but it only assures you one axis of movement with one control and smooth air. So if we went full back on the elevator below VA, yeah, we're not going to break the aircraft. But if we went full elevator back and full right rudder at the same time, you can rip your tail off. So it only gives you one axis of movement in smooth air, pretty much. Cool. So that's going to be airspeeds, altitude. Know your V speeds before we jump into this. And that's going to basically be the other video. We're going to go into the performance charts and get a good idea of why we need to know this stuff, why it is so important to keep us and our passengers safe. But thank you. All right, so what I have here is the Pilot Information Manual for the Skyhawk 172 SP, or the model 172S. This is going to be a generic pilot operating handbook. It is a pilot information manual, so it is not specific to our aircraft. How do we know it's not specific to our aircraft? It does not have our tail number anywhere here. When we're flying around with the pilot operating handbook, we have to make sure that our tail number is specific to that handbook itself, and we don't have just this generic pilot information manual. So we just finished up on performance and what is pressure altitude, what is density altitude, how that affects your performance. This is all in reference to Chapter 5 of this pilot information manual. So I'll go ahead, we'll go down through here, just shooting through the limitations, emergency procedures, checklists. This is just the lifeblood of the 172S. But again, has to be specific to your aircraft, so make sure that you're flying around with the actual pilot operating handbook, not this generic one. So, Section 5, performance. We're going to have an introduction, the use of performance charts. They'll give us sample problems. Now, when we come down into here, we'll talk about airspeed. We'll talk about the difference between indicated airspeed and calibrated airspeed, how using the alternate static source affects that, and all that stuff. Then we're going to go into stall speeds and different configurations, crosswind components. But the main thing we want to talk about here is the short fuel takeoff distance, maximum rate of climb, time, fuel, and distance to climb, cruise performance, range profile, endurance profile, and short field landing distance. So this is basically like a simulated flight. To start the flight, we have to go ahead and take off. Well, we're going to use a short field takeoff technique per the pilot information manual, which is going to be a different V speed, or a different speed we actually rotate out and climb out at. It's just kind of a max performance takeoff. And then we're going to have to climb. What kind of climb speed are we actually going to get, or climb performance, based on different pressure or different temperature for a given day? What is going to be our time, fuel, and distance to climb? What's going to be our cruise performance? How fast are we going to go? Our range profile, what kind of fuel we're going to burn, all that stuff. And then the ground roll, short field landing distance. After we clear that 50-foot obstacle, how much runway are we actually going to chew up? So go ahead and go down. We'll just pass the introduction and the performance chart, or the sample problems and whatnot. We'll start at airspeed calibration. This is what I was talking about when we were going over airspeeds just a second ago. So we'll have an indicated airspeed. We have a flaps up setting. Indicated airspeed is going to be 50 knots, but because of instrument error, position error with that pitot tube, it's actually going to be 56 knots. So kind of a little bit of a nice buffer for you. As we go up in airspeed, though, it kind of trades out. At 90 knots, we're actually flying 87. But at these slow airspeeds, it actually gives you a little bit of a buffer. If we go to flaps 10, if we're at 40 knots, that is our VSO, our stall speed in a landing configuration, we're actually flying 51 knots. So just some things we got to be aware of. This is going to be the conversion chart, and we'll use that when we're doing navigational flight planning. We'll go from indicated airspeed to calibrated airspeed. Just some alternate static source, temperature conversion chart if you ever want to go from Fahrenheit to Celsius. Stall speeds with different centers of gravity. We'll go over that when we jump into weight and balance. How we distribute weight inside of the aircraft is going to affect our stall speed and performance characteristics as well. Wind components, crosswind components. This will be in your written. Just understand how to use those charts. It's pretty simple. Kind of hard to show you without going line by line with you, but this is where we could reference to get a good idea what a crosswind component will be, or a tailwind or a headwind component. Now we have the short field takeoff distance at 2,550 pounds, which is the max gross weight for the aircraft. Now we have a few different charts for our takeoff, where we're starting our flight. This takeoff here, we have a short field takeoff distance at 2,400 pounds, and we have a short field takeoff distance at 2,200 pounds. Obviously, being at max gross weight, we're going to chew up more runway. So this is the chart for us to use if we want to be conservative, because these charts were made with a test pilot and a brand new aircraft. We have to understand that our aircraft coming from the 90s has got some wear on it. It doesn't perform like it first did right out of the factory, and we're also not professional pilots, so we kind of have to put a buffer in there. So we'll use the short field takeoff distance at 2,550. We'll be chewing up more runway, and it's just kind of a conservative factor. Whenever we're using these charts, we want to be extra conservative, just because it's not a brand new aircraft anymore, and we're not a professional pilot. That's where these numbers were derived from. So whenever we're using these charts here, we have to go over two things first: the conditions, which is going to be on the top up here, and then we have to go over the notes. Those are the first two things that we're going to go ahead and read before we actually use these figures. So conditions: flaps 10 degrees. That's going to be standard for a short field takeoff. Full throttle prior to brake release, so us using the most amount of runway at 10 degrees flaps, applying the brakes, going full throttle, verifying our engine instruments are in the green, and verifying that the airspeed is actually staying at 0. And this is a paved level dry runway. If we're using a grass strip or a dirt strip, obviously these numbers would be increased. This is in 0 wind, so if we had a headwind, these numbers would be decreased a little bit less, because a headwind allows us to take off in a certain amount of ground roll, and a tailwind would do the vice versa of that, so it would decrease our performance, and we chew up more runway before we actually got to a good liftoff speed. Liftoff speed is going to be 51 knots, so a little bit lower than our regular VR, our rotation speed. And then speed at 50 knots, or climb out speed, is going to be 56 knots until we climb that obstacle. One thing that people don't really understand is these liftoff speeds and these climb out speeds are going to change with weight. So if we go down to 2,400 pounds, we have a liftoff speed of 48. and a climb out speed of 54 there. And then we have at 2,200 pounds, a liftoff speed of 44 and a climb out of 50. So it kind of changes with weight. But if we want to be extra conservative, we're going to use the 2550, which is pretty standard. But just know, for your check ride sake, that it does actually change with weight. So liftoff 51, climb out 56. Now let's read those notes, because like a good pilot, we read the conditions first, then we go to the notes. Short field techniques as specified in section 4, so just standard short field takeoff techniques. Prior to takeoff from fields above 3,000 feet elevation, the mixture should be lean to give maximum RPM, so above 3,000, we're going to lean it out for best RPM. Decrease distances 10% for each 9 knots of headwind. For operations with tailwinds up to 10 knots, increase distances by 10% for each 2 knots. So we have to go ahead and change the numbers that we get for each 9 knots of headwind, 10%. So we have to decrease it. Like we said, it's going to decrease our ground roll if we had that headwind. It's letting us know that. And then for operations with tailwinds up to 10 knots, increase those distances by 10% for each 2 knots. So if you had a 4-knot tailwind, you'd have to increase these numbers by 20%, which is going to be quite a bit. And then for operations on dry grass runways, increase distances by 15% of the ground roll figure, which is huge. So of a dirt or grass runway, we know the conditions for this is a paved level dry runway. We have to go ahead and increase it by 15%. So the ground roll is going to be pretty big. Cool. Now we can go ahead and jump into the chart itself. Like I said, when we were calculating that pressure altitude, we were doing that for a reason. We have sea level here. We have 1,000 feet. We have 2,000 feet. The last calculation that we did for a pressure altitude, with the altimeter setting being 3002, was 900 feet. But if we want to be conservative, let's just round up a little bit, and we'll call it 1,000 feet. Now, temperature. We said that Phoenix was going to be 105 degrees Fahrenheit for the day, which is going to be this 40 degrees Celsius column all the way out this other side. So we're correcting for pressure in this left column, and in the top row, we're correcting for temperature. So pressure on the left column and temperature on the top column. And we're just going to kind of line them up. So 1,000 feet, we're going to go, we have 2 things here. Ground roll, so the actual runway we're going to chew up. And then total feet to clear a 50-foot obstacle. This is going to be our horizontal distance it actually takes for us to climb up at that 56 knots. Get above that 50-foot obstacle, it's going to be 1,600 feet. But we have to go to the 40 degrees Celsius column. So we'll go all the way over here. Now we can calculate... just make sure we're using the right one here. So at 1,000-foot pressure altitude and at 40 degrees Celsius, we are going to have a ground roll of 1,260 feet. And then to clear that 50-foot obstacle, we're going to need a horizontal distance of 2,135 feet. And that's basically how we're using the short field takeoff performance charts. As you can see, as our pressure altitude goes down, say if we were taking off at an airport at 8,000 feet, I forget how much Flagstaff actually is. I know it's pretty high up there. If we went 8,000 feet and we went all the way to the hottest day it could be, we're going to use pretty much double. So 2,450 feet is going to be our ground roll to actually get to that rotation speed. And to clear that 50-foot obstacle, we're going to need 4,600 feet. So if we have a tree that is, 4,000 foot down the runway and it's 50 feet, we're probably not going to make it. So this is why it is so important to understand your runway lengths of intended use, because this is going to save your life. It really is. Cool. So this is going to be takeoff. So this is using a short field takeoff technique. And then we have the different weights as well. Like I said, be conservative. This was done by a test pilot in a brand new aircraft. So use the highest gross weights, round up your numbers. If it's warmer, or if that pressure altitude's a little bit higher, use that higher number just to make sure that you're giving yourself a little bit of a safety buffer, because this is no longer a new aircraft. Let's go down here. Now we have to climb. So this is going to be maximum rated climb at 2,550, so max gross weight. They don't have another one that varies with the weight that we actually are. It's just max gross weight 2,550. Conditions, flaps up and full throttle. So if we were using that short field takeoff technique, we would not be getting this climb performance because we were flaps 10. And this is also full throttle. So we got to be full throttle to get these actual figures. Notes, mixture leaned above 3,000 feet for maximum RPM. And we'll talk about correct leaning procedures when we're actually flying around. But yeah, it's lined up kind of like the short field landing technique was. So pressure altitude is going to be the left column, and on the top column we're correcting for temperature. So pressure altitude. We know density altitude is pressure altitude corrected for temperature, and these are the figures that we get. So we have, let's say we're taking off at a pressure altitude of 1,000 feet like we were. You notice we don't have that figure. We actually have to interpolate to get the actual number. So if we go ahead and we have sea level to 2,000 feet, so we go from 560, if we go all the way up to the temperature, which is 40 degrees Celsius, we have 560 and 645. So we know at sea level, we'll get in feet per minute if we climb out 74 knots, 645 feet per minute on the VSI. And then if we're climbing out 2,000, it'd be 560 feet per minute. We have to find the average of this because we're actually taking off at a pressure altitude of 1,000. So we'll go 645 plus 560, which will honestly put us around 600 feet per minute. And as we climb, as we go up and up, we see 4,000, 6,000, 8,000 feet. We see that it starts to drop because less dense air, less air for engine thrust or engine power, less air for propeller thrust, and less lift over the wings. So you can see how, at 4,000 feet, at 40 degrees Celsius, 495, as we go down 390, 285, 180, until we get to a service ceiling where we actually can't climb anymore. Just a good note there. Next one, time, fuel, and distance to climb. How much fuel we're actually going to use, how much time is it going to take us to actually get to our desired altitude, and how much distance we're actually going to go ahead and chew up. This will be very important when we go into our navigational flight planning, when we're going over a nav log or top of climb. We're going to need to know how far that top of climb in a horizontal distance is actually going to take us, and this is the chart that we can really use for that. So we'll start at the pressure altitude here. 1,000 feet, and then a climb speed of 73. Rate of climb is going to be I committed I forgot to read the conditions first. So conditions: flaps up, full throttle, and it's standard temperature. So that's why if I just use that chart, this is a great example of using the charts incorrectly. I just started reading it. We have to know that these are in standard temperature conditions. So if we go to the notes, it's probably going to have some information on that. Add 1.4 gallons of fuel for engine start, takeoff, and taxi and takeoff allowance. Mixture leaned above 3,000 for a maximum RPM. Increase time, fuel, and distance by 10% for each 10 degrees Celsius above standard temperature. So when we were taking off in 40 degrees Celsius at that pressure altitude of 1,000, and we know standard temperature for that was actually 13 degrees Celsius. Each 10 degrees Celsius above standard, that's almost going to be 30 degrees above Celsius. So we'd have to increase these numbers by 30%, all the time, fuel, and distance by 30%, because we're almost 30 degrees above standard temperature. So just to be aware there. Distances are shown based on zero wind as well. So if we had a headwind, it would go ahead and decrease that distance. Obviously, if we had the tailwind, it would push us out further. Also, with a headwind, we get better climb rate and whatnot. But yeah, so we read the conditions, we read the notes. Now we can go ahead and jump into this. So pressure altitude of 1,000 feet. We'll start with that left column there, climbing out 73. Rate of climb is going to be 695 feet per minute. Time is going to be 1 minute. Fuel use 0.4. Distance 2 nautical miles. What does all that mean? Well, that's telling us if we were flying from sea level to 1,000 feet, we would get a climb rate of 695, and it would take us 1 minute. We would use less than a half gallon of fuel, and it would take us 2 nautical miles to get from sea level to 1,000 feet. But we're flying from sea level and we want to go to a cruise altitude of, let's say, 6,500 feet. So what we're going to do is we're going to start out at that 1,000. We have those figures there. Then we're going to go to 6,500 in the pressure altitude. Look at that. We don't have 6,500. So we can just kind of round up to be a little bit more conservative, and we'll use the 7,000 figure. We could interpolate, use the averages between those numbers. Just a lot of math, a lot of time, and it's just going to be kind of marginal. So we'll just use the higher figure just to be a little bit more conservative. So it's 7,000 feet, 73 knot climb speed. Rate of climb is going to be 455. And then we have, which we could actually get the climb rate from 1,000 to that pressure altitude of 7,000. We could average those out and get our climb rate along the way. We could do that. But once we go over to time in minutes, so we'll go from 12 minutes from sea level. We're not flying from sea level. We're flying from 1,000 feet pressure altitude. So what we're going to have to do is go 12 minus the 1. And that means that it's going to take us 11 minutes to get from 1,000 feet pressure altitude all the way up to a cruise altitude of 6,500. We're using 7,000 to be conservative. Now, if we go to 2.6, we have to use 2.6 minus the 0.4. So it's actually going to take us 2.2 gallons to get from 1,000 to 7,000. And now we have our distance in nautical miles. So how long is it actually horizontal distance? How far is it going to take for us to actually get to 7,000 from 1,000? We go 16 minus 2. So it's going to be 14 nautical miles. Now, we know that we have to increase these by 30%. I don't have a calculator on me, but you would go through each figure and multiply it by 1.3. You know, you take that 12 minus a 1, 11 times 1.3, 2.6 minus 0.4 times 1.3, and then 16 minus the 2 times 1.3, and you get the actual figures for your time to get the altitude, the fuel that you're going to use, and then the distance in nautical miles. And just a heads up, like the notes say, this is based off of zero wind, so it can vary. But yeah, that's going to be time, fuel, and distance to climb. That's kind of how we use that chart. And that's at 2,550 pounds max gross weight. We don't have another weight for this one. All right. Now we can go to, say, we got to this cruise altitude of 6,500 feet. What kind of performance are we actually going to get there? So first things first, we're going to read the conditions. 2,500 pounds, 550 pounds, recommended lean mixture at all altitudes. So just, lean the mixture for best performance. And as we go down here, we get higher and higher pressure altitudes. So we can go from here. We know our pressure altitude that we wanted to fly to was 7,000 feet or 6,500, but we don't have that. We have 6,000 pressure altitude and we have 8,000 pressure altitude. So it kind of skips that for us. Now, we have to understand the notes as well. No notes for this one, unfortunately. We just have the conditions for it. But we're going to have to do some interpolation from the 6,000 to the 8,000. And we know we're 30 degrees Celsius above standard, but this says 20 degrees Celsius above standard. So we actually might be flying a little bit faster because of that less dense air as we go up in altitude. And we might be using a little bit more fuel as well, or less fuel as well, because we have that better cruise performance with that less dense air. So we go from, let's look up here, what RPM setting are we going to fly at? So we'll start from 2,000 just to break it down. So RPM, 2,550. We got 2,500, 2,400, 2,300, 2,200 RPM, and 2,100 RPM. It's recommended not to cruise around. You won't be redlining this engine. So we want to pick a suitable RPM that's not going to overstress the aircraft. We are rated at that, a little bit higher than that, but we don't want to overstress the aircraft. So we go to the right here. Let's look at the temperature. So 20 degrees Celsius below standard temperature. We're not that, but let's see what that percent brake horsepower is. Percent brake horsepower, yeah, our RPM is 2,550, and we're rated for 2,700 RPM, but we're actually only getting 83% brake horsepower, or the 83% power, opposed to 100% power. Kind of impossible to get 100% power with drag, the air mass itself, all that stuff. So this is just the actual percent of power you're actually going to get out of it. That's what it's showing you. We will go down to the true airspeed. So at 2,550 RPM, we'll get a true airspeed of 117, which is going to really help us out when we're trying to manage or calculate our estimated time en route. And then we have the gallons per hour, so how much fuel we're actually going to burn. So that's at a pressure altitude of 2,000. We wanted to come back up to our 6,500. We can use 6,000 just for simplicity here. I could show you the math. We could interpolate between the 6,000 and the 8,000, but it's just a lot of math at the moment, so we won't do that. So we have to pick a good RPM setting, I would say 2,500 RPM is going to be good for cross country. We don't want to be pushing above 65% brake horsepower for extended periods of time, or I believe it's 75%. I'd have to double check that. We just don't want to over stress that engine. So anything below, that 75% brake horsepower is going to be a good power setting for us. So we can go, 65% horsepower, brake horsepower. So we'll go ahead and go 2,400 RPM for the 6,000 because that puts us at 62% brake horsepower. It's going to give us a good cruise speed if we're 20 degrees below standard temperature of 109. And then we have gallons per hour, 8.6. But we know we're 20 degrees Celsius above standard temperature. So if we go all the way to the rightmost column at 2,400 RPM, we will get a brake horsepower of 54%. We'll also get a true airspeed of 106, and then we'll also get a gallons per hour of 7.7. We can actually bump it up to 2,500 RPM because our brake horsepower is still under that 65%. We're getting 60% brake horsepower here. True airspeed's 112, and then gallons per hour is going to be 8.5. So that's going to be our fuel burn for it. Now, when we go to a navlog, we can actually calculate how long each checkpoint is going to be to get to A to B, what brake horsepower we're at, and how many gallons per hour we're actually going to burn, which is super helpful. Now we can go down here, so we can see here, now we can come down to our range profile. This is just letting us know our range in nautical miles, how much we're going to get with the brake horsepower we actually choose. So conditions, 2,550, recommended lean mixture for cruise at all altitudes, standard temperature, and 0 wind. Notes, this chart allows for fuel use for engine start, taxi, takeoff, and climb, and the distance during climb. So we picked 65% brake horsepower. If we go ahead and follow that line, and we're at 7,000 feet. If we go up to that line, we know our range in nautical miles. If we were full fuel, it would be about 550 nautical miles if we went down. This is assuming that we have 53 gallons of usable fuel with 45 minutes reserve. So if we just spent all the fuel out with 45 minutes of fuel left and we filled it up all the way 53 gallons, because we know we have 56 gallons, we would get 550 nautical miles out of it. Just a heads up, nothing you ever want to do, but just kind of showing you the performance of the aircraft. And then this is just the endurance, so we know we can go 550 nautical miles if we bled all the fuel out of the engine. This is showing you if you bled all the fuel out of the engine, with 45 minutes reserve, so that would be 3/4 of an hour of usable fuel, and then you filled up all the tanks and you just bled it all the way down to that reserve. At 65% power, it's going to give you about, and you're at a cruise altitude of 7,000, 6,500, be a little bit less than 4 hours. So that's basically what that's showing you there. Read the conditions though. 2,550 pounds, standard temperature. Honestly, these charts aren't super important, the range and the endurance. It is very important to understand how much fuel you're going to burn in gallons per hour, but we're never going to bleed it out with a 45-minute reserve. We can go ahead and calculate that without these charts. So cool. And then we have to land. So we cruised. We took off. We got the climb rate. We know the fuel it took to climb, the nautical miles, how much time it was going to take. Then we got to cruise. We got our true airspeed. We understood our gallons per hour, how much fuel we're going to burn, and our brake horsepower. Now we got to land. So we got to pick a runway that's going to allow us to do that. So it's going to allow for a ground roll. So let's say we're doing a flight, out to Yuma. I can't think off the top of my head what the elevation is out there. I believe it's probably around 1,000 feet, 2,000 feet. But we'd have to calculate the pressure altitude to understand our ground roll there. So this is short field landing distance at max gross weight. Our conditions are flaps 30 degrees, so full flaps. This is power off, maximum braking as soon as we get those wheels on the runway. Pave, level, dry runway, 0 wind. So headwind would decrease this, tailwind would increase this. Speed at 50-foot obstacle, 61 knots. So our approach speed is going to be 61 knots in this scenario. Short field landing techniques as specified in Section 4 on the notes. Decreased distances 10% for each 9 knots of headwind for operations with tailwinds up to 10 knots. Increased distances by 10% for each 2 knots. So that's a lot. If you're landing, this is why we always land in headwinds and not tailwinds, because we start eating up a lot of runway with the tailwind. For operation on dry grass runways, increased distances by 45% of the ground roll figure. So that's a lot, 45% if you're landing on a grass or a grass runway. So you have to bump up that figure a lot. And then if landing with flaps up, increase the approach speed by 9 knots and allow for 35% longer distances. So, if we had that flat failure and we had to land flaps up, we'd have to go ahead and increase our approach speed, which is going to increase our landing distance by 35%, which is huge. So now let's assume, we'd have to go ahead and calculate the pressure altitude at our landing airport. In the scenario, we didn't go ahead and do that. We'll just assume it's also 1,000 feet. Pressure is not going to really change. The big thing is temperature. So we have to get an idea of what the pressure is, and then we have to know what the temperature is to really use these charts. But we'll just assume that it's a little bit colder out and humid today. Let's say it's 30 degrees Celsius, and we'll use the 1,000-foot pressure altitude mark. So we'll just read it like we did this short field takeoff. We'll go from 1,000 feet pressure altitude here, and then we'll go all the way to 30 degrees Celsius. We know our ground roll is going to be 625 feet. Total feet to clear the 50-foot obstacle. So once we clear that 50-foot obstacle, the theoretical one in front of the runway, if there was one, we need 1,420 feet. But the big one here is our ground roll, 625 feet. So we need a runway that's going to go ahead and allow for that, which most runways do. But this is assuming that it is a zero-wind situation. So if we had that tailwind, we'd have to increase this. If we had a grass runway, we'd have to increase this by a lot. If it was a pressure altitude of 8,000 and temperature was 40 degrees Celsius, it would go to 840 feet on the ground roll. But yeah, the biggest factors would be, hey, are we landing in a headwind or a tailwind? Is this a dry grass runway? Are we flaps up? What is our approach speed? Because once we start bringing up this approach speed from 61 knots, if we fly anything faster than that, these ground rolls increase drastically. And, this is where those, runway incursions happen. Those situations where people run out of runways and go into fences, trees, obstacles, cars, other people. So this is a huge reason why we use these charts to keep us and our passengers safe, really. This is part of our 91-103 pre-flight action, is to get an understanding of these charts, our pressure altitudes for our departure airport and our arrival airport, also the density altitude, so the temperature at those airports, and what kind of performance we're actually going to get. If we go through that NW craft, we go takeoff and landing distance data. We have to understand that. We also have to understand for a given day, our cruise performance is going to change. We're burning more fuel, less fuel, we're going faster, we're going slower. And that's drastically going to affect how we plan for this flight, how much fuel we're going to bring, and how much time we think it's actually going to take us to get there. So that's going to be Chapter 5, the Pilot Information Manual. This was just a brief overview of it. Go ahead, do some sample problems, jump through it. This will 110% come up on your check ride. It will ask you how to use these tables, give you a scenario with pressure, altitude, and temperature, and have you calculate the ground roll for a takeoff or a landing. What's your cruise performance going to be? What are all those conditions notes mean? Just go through it, become very familiar with it, because it might save your life one day. But yeah, that's going to be performance. We'll go into limitations in the next video, and that's going to be weight and balance, how we distribute weight in the aircraft, how that affects our stall speed, how important it is to be in the center of gravity envelope. That's going to be the gist of the next lesson. But that's performance. Thanks.